We're now going to be looking at pose-based deformation. When we're talking about pose-based deformation, we are generally talking about the use of blend shapes that are applied to a deformed mesh in order to correct volume or deformation issues. There are some slight technicalities here, but the implementation is actually relatively simple. The problem that we need to deal with is this. When we deform a mesh with a skeleton, there will be areas around the joint where the deformation is not ideal. Usually the inside of the joint will compress badly, either that or we will have pinching, and the interpolation around the outside of the joint will lead to a flattening of the outside of the joint. There are numerous ways of dealing with this, and in this case we are going to be dealing with it by creating custom poses. So we will add shapes to the deformation. We'll then blend those shapes with the deformation based off the angles of the joints for the rig. We'll create the shapes after we've created the deformation, but for the final rig we'll actually want to apply the shapes before the deformation. So generally this process will be performed in multiple stages, and it is usually best to separate these stages. First we'll look at modeling our shapes. There are a couple of nodes which we can use to model the shapes in Houdini. The first of these nodes, and the most obvious one, will be the Edit node. This is the default Houdini node for modifying geometry. I'll activate the node by pressing Enter in the viewport. I will select a point. I can then turn on my soft radius. If the fall-off is not shown in the viewport, we can activate the visualizations. By default, there will be a soft fall-off visualization here, and you can make sure that this is activated. I can then select and modify my geometry. This is not a particularly pretty deformation, but it will give you an idea of how this will work. There are other options for modeling. The main one after the Edit node would be the Polydraw node. This is a variant of the Topo Build node, however it does not require source geometry and will allow you to model rather than just do retopology. There are a number of tools which we can use within this to edit geometry. In this case we would mainly use the brush tool. We would also use the smooth tool. As with the Edit node, this is not particularly pretty, but it will serve the role of an example well enough. Very often we wouldn't even want to do the modeling within Houdini in any case. As with more detailed poses, we generally want to export the mesh to a modeling package like ZBrush or Mudbox. So we've modeled basic poses to test with, and we can take a look at some of the things which you'll need to pay attention to, as well as potential problems which you'll encounter with pose-based deformation setups. Now I can disconnect both of these nodes from the deformation, and we'll notice that these nodes behave differently. Firstly, the Edit node will not work without an input, and if the Edit node is connected to the mesh before the deformation is still applied. There are, however, issues with this deformation that we should be aware of. The Edit node stores the operations as global translations. While it may appear that this node is giving us the change in position of the points, this is not actually the case. In this case, I'm getting the translation of the points. I am not getting an absolute delta. The result of the Polydraw node is different. This node caches the entire mesh as well as the deformation. So here we have retained a copy of all the deformation which we've created on the mesh. This is essentially a similar situation to what we'd get if we exported the deformed pose to a package like ZBrush and then made the shape there. So we've got poses which we've created, and now we'll actually want to apply these poses. And these poses will generally be applied with a blend node. The first input will be set by our original geometry, and this is the geometry which we want to deform. The second input is multi-input, and this can take multiple blend poses. We can perform this blend before or after the deformation. When possible, it is best to perform this before the deformation, as this is far more flexible. This allows you to separate the deformation from the rig and retain the poses at the same time. Currently our pose is connected after the deformation, and there are numerous problems with this. The biggest problem that we'll encounter here is that of the deformation overriding the animation. Here the blend for the Polydraw node is working correctly. However, if we scrub the animation, we'll see that no animation occurs. We will get a better result with the Edit node. This is because we're blending the final transformations for the node. This is blending the final translations. So if we only store the final translations, we can get a workable blend doing things this way. We can also get this transformation mathematically by using a subtraction of the final pose from the final pose modified by the shape. This method of taking the transformation difference of the final pose is not the method which I'm going to be focusing on, but it can work. We should, however, note that we cannot do both. We will have different issues with this pose if we try and apply it before the deformation. So we can calculate these blends before we do the deformation, and here we'll have different issues. The first issue here would be with the edit node. When we apply this after the bone is deformed, we are purely calculating the translation of these points from the final pose. While it does appear that calculating these poses off the original pose deforms this correctly, when we apply this beforehand, we'll see that there's an issue with the deformation. If we look at this deformation more closely, we'll see that this is not an accurate deformation. We will discuss why this is happening a little bit later. For the poly draw, this will not work at all, as we'll get a doubling of the deformation. So for this style of deformation, we can ignore the poly draw for the moment, and we can look at the edit, and we'll look at the information that we really want from the shape. To do this, I'll get a duplicate of the edit node. The ideal information to have is what is called the delta. This is where we get the full change of position for the points at the end of the deformation, and getting the difference between these positions and the mesh at the original position. We then want to take this change in positions and we want to apply this to the original mesh. In this case, merely adding the translations, like we have with the edit node, will not work. For this to work, we need both the change of positions for the deformation as well as the change of positions within the shape. Essentially, the deformation changes the space of the transforms, and we need to remove the effect of the transformations based off this space in order to get a proper delta. Now we'll look at how we can compensate for the complexities of the deformation in order to extract a correct delta. There are a number of ways to do this, and the methods which I used originally were very complicated. So in this case, I'm going to be using a method which I first saw published by Rock Andek. This is very straightforward, so I will stick with this method. I do think this is one of the most straightforward methods for doing this. So initially, we'll need to add an attribute to the mesh. I'm going to add this before we capture any of the weights on the mesh, and in this case, I'm going to do this specifically with an attribute create node. I'll call this attribute pose transform. This attribute will be a 4x4 identity transform. This will be a point attribute and it will be a float attribute. As this is a 4x4 matrix, this will be of size 16. Then we'll need to change the type of this attribute. If we do not change the type here, this will not work. We need to explicitly state that this is a transformation matrix. If we do not change the type to transformation matrix, we will not be able to use this attribute. Next, I will want to make sure that this matrix is initialized as an identity matrix. To do this, I'll get an attribute wrangle node. This attribute should be a 4x4 matrix. So we'll use for at pose transform. I'll then set this to be an identity matrix, and I'll do this with the ident function. In the geometry spreadsheet, we should now have the pose transform matrix. We can now use this matrix in the bone deform node. In the bone deform node, there is an option called other attributes. We're going to set our pose transform here. We'll not be able to set our pose transform node here unless we explicitly state that this is a transformation matrix. This is why we need to set the type in the attribute create node. Placing an attribute in the other transform will allow the attribute to be deformed as well as part of the mesh. This way we can use the attribute to store the actual deformation for each point. So now if we look at the geometry spreadsheet, we should see that we have stored a transform for every single point. This transform should be updated as we update the deformation, and we can use this information to get the delta for our transform. So I'll use this to get the delta from both my poly draw and my edit node. I'll do this using an attribute wrangle node. The first input will be set by our deformed geometry with the shape added. The second input will be set by the original deformation. So the first thing that we're going to do is we're going to invert the transform. This will allow us to nullify the original mesh and only leave us with the difference. So essentially we can use this to undo any transformations to the original matrix. I'll store the inverse in a matrix variable. I will call this variable IM. We'll set this using the inverse function, and I'm going to get the inverse of the pose transform attribute. We'll get this using the point function, because this is a point attribute. We'll be getting this from our second input, so the input number will be 1. The name of the attribute will be pose transform. We'll get this from the current point using @ptnum. We can now use this to get our delta, and we're going to store our delta in the point position. So this will be @p. We'll get our deformed point position, and we'll multiply this by our inverse matrix. We should now have a proper delta. If we look at the delta when we have no deformation, we should see that this is actually different from the shape that we get when we have no deformation and are only using the transformation node. That is because the delta represents a final change in position. This is an accurate delta, and this is the delta which we want for all of our transforms. This approach will work for our polydraw deformation as well. We'll attach an attribute wrangle, and we'll put the polydraw into the first input. The second input will read from our deformed mesh. This will also give us an accurate delta. This method of getting the delta does not only work in Houdini. It is also an approach which you can use with geometry which has been edited in an external application. We will look at that as well as applying the data in the next video.